Hi everyone, welcome to the final part of my video on causal graph, backdoor and frontal criterion and dual calculus. In this part, we're going to talk about dual calculus, and perhaps is the most interesting part of this video series. Um, dual calculus is being discussed in the internet maybe in 4 or 5 websites, and to me, none of them are clear because it's a mathematical concept, and most people don't really understand it. And so people try hard. Not that they don't try hard. There are some good resources out there. But to me, is that they're just mathematical expressions. To many people, they're just very abstract concepts. Causal inference is the future, in my opinion. After we have right now a lot of exciting stuff with LLM and stuff, but causal inference is the future, and has lots of numerous application in the industry. And guess what? Majority of data is observational data. Not all industry has the power and resources to run experiment, A/B testing. So observational study is actually here to stay. And for that matter, it's very, very important to have a good foundation on causal inference. In the first part of this video series, part one, we talk about the concept of confounders. We talk about the concept of causal graph. We talk about backdoor path. We talk about do calculus. Not do calculus, sorry. We talk about do operator. And etc. In part two, we talk about backdoor and front door criterion. Great. Now, part three, which is this part, we're going to talk about do calculus. All right. So what is do calculus, guys? What is do calculus? Do calculus they are set of rules that let you start from expression containing two operators and deriving final do free expression. So do calculus is a set of manipulations, set of rules that lets you come up with a final do free result. And so when I say set of rules, in a sense, there are 3 rules developed by Judy Appert, right? And they can be applied to any graph, any complex graph. It's not like similar to backdoor and frontal criterion. You can derive backdoor and frontal criterion using do calculus. I perhaps will derive backdoor criterion using do calculus for you guys, right? And now about the do calculus is that you can apply to anything you like. So you apply these rules over and over again until the final result does not contain any do operator, does not contain any do operation. Now, if you apply this over and over again and still the final result has a do operation in it, this means that your graph is not identifiable. Your problem is not identifiable. And if applying the do calculus over and over again does not lead to do free result. This means that problem is not identifiable, not sufficient information. All right, great. Now let's get to the actual main part. All right, so do calculus set up 3 rules that allows you to start from the expression with do, and then do some manipulation, either to remove some variables, add some variables, or remove the do operation for some of the variables. But the main goal is that when Perl created is that if you want to calculate the causal effect of x on y, you have a do in it. At the end of the day, when you want to calculate the result, you have an observable quantity, not do. So you need to apply this do of calculus to actually get the do-free expression. All right. So rule number 1. My goal is to give you intuition to understand these rules. Otherwise, these rules exist in the Judea Pearl textbooks and also exist in the paper as well. My goal is to make it easily understandable by everyone. That's my goal. So rule number 1. It's called insertion and deletion of observations. All right, that's what pretty much it is. Insertion and deletion of observation. What does it mean? It means that if I start with P of y, given do of x, intervention on x, w and z, under certain condition, which I will tell you, I can get to P of y, do x, and w. You see, I remove z. Z is observation. I remove z. Then, if y given y is independent of z given x and w, in what graph? In graph of g x bar. I defined this one in the part 1 of the video, in my first video, but let me just define this one. If you have a graph g as follows, z x y, this is graph g, g x line above. Remember I told you the line above, think of it as a parent, right? This means that take the graph g and remove any edge that points to x, that goes to x, that come from the parent to x, right? So here, for example, you have z, the z edge going to x, we remove it. We don't need it. That's this. And then we have another one, g line under x, which says that take the graph g and remove any edge that is going out of x. That is going out of x. So you have z, x, and y. All right. Those are the 2 things that Perl actually defined. All right. So now that we understand this, it says that this expression is valid if you take a modified graph and remove any edge pointing to x, and then after that, you realize that y and z are de-separated given x and w. Let's take a look at an example. Let's take a look at a graph here with each other. A little bit more complex graph. Z, w, x, this goes here, this goes here, this goes to y, and then this goes here. All right. So I start with this, guys. P of y given do x, z, and w. All right. So what this expression says is that, you know what? Create a graph. This is graph G. Create a graph G x bar. Go ahead and remove any arrow that points to x in graph G. What does it mean? It means z, w, x, y, and that's it. W is pointing to x. Go ahead and remove that. All right. Now tell me about this. In this graph, is y and z de-separated, or is y and z independent given x and w? Let's take a look at that. There is 2 paths from z to y, right? This path, if you follow this path, if you condition on x, they are independent, right? You close this path. And then we have another path, this one. If you condition on y, this path also is closed. So then yes, y and z are independent given x and w on this graph, Therefore, what this theorem says is that you can drop z. You can get a z free formula. So that's what this expression says. All right, so that's what it says. But how do I think about this? I think it's very important to have this intuitive understanding of causal graph. How do I think about it? This is how I think about this, guys. I think I don't even need to know this rule. That's what I think. When you say do x in the first part of the video, definitely go and watch it. I told you that when you apply do x, this means that you go ahead and remove the edge going to the x. That's what do is. See, I make an intervention. I don't care what the parent says. I want to set the value of x to little x. I don't want the parents tell me what the value of x should be, what the distribution of x is. I want to set the value of x to little x. I want to make an intervention. All right. So I am going to copy this graph. And paste it here for you. All right. And then I'm going to write this expression again. I'm going to tell you how I look at this problem. I don't even look at the rule here. Z and W. Okay, if there is a do x, step number 1, go and apply the graph G2. Z, W, do x, remove the edge from the parents. All right. Is that correct? All right, now we have this expression. Guys, from your probability class, you know that if you have P of y given x, if y and x are independent, what do you get here? You get P of y. What does it mean? It means that if I tell you, if I know about x, it doesn't tell me any information, more information about y. Because they are independent. It doesn't really matter. So the same thing here. Search for any variable that is independent of y. Condition on others. This is x variable. Condition on others. Is y and w independent? Absolutely not. There is a direct path between them. Is y and x are independent? No. Is y and z are independent given x and w? Yes. That's it. I don't need to know that rule. I don't need to know that rule. I can do it immediately. All right, so that's rule number 1. Let's go to rule number 2. Now, rule number 2 is in my opinion, is the most interesting one. And it's perhaps the hardest rule to understand. All right. So rule number 2 is about exchanging action and observation. That's what exactly we are doing. Action, observation, exchange. All right. Okay, what is action? Means treatment, means intervention, means do. I want to change the do to see. Means I want to get rid of the do, right? Remember I tell you in the first part, P of y given x means probability of y seeing x. That's what your supervised learning models do. That's what your discriminative classifier is doing, right? I want to get from this one. This is intervention, this is action. Okay, great. Now that we understand this, let's take a look at what this rule says. This rule says probability of y given do x, do z, and w is equal to probability of y given do x. I'm gonna exchange action and observation z and w. If y and z are independent, given x and w, in graph that I remove the parents, remove the edges going to x and edges coming out of z. Okay, in this graph. If this condition holds, I can do this. Now, how do I think about this? How would I think about this one? Let me see if I can come up with a graph here. If I have a z here, and if I have this one here, let me just show another here. These rules apply to anything, to be honest. So you don't have to really w x y, and then I can plot this one as well. Yeah, similar to what we had. W going to Z. I switched some of the edges here. So now let's take a look at this one. Let's first understand this rule. Wait, let's construct this graph. Gx bar Z is this one, given that this is G. Remove all the edges going to X, remove all the edges out of Z. Z is completely isolated. Oh. W, X to W, X to Y, and this. Are they independent? Is Y and Z independent? Yeah, that's it. Because all the edges that are going out of Z, we have to delete it. And Z and Y are independent. They are actually not connected. Z is independent of anything else. So that it says that you can actually remove do Z with Z here in this graph. Let me see how I look at that. I'm saying that this is very hard to convince us, but I'm saying that these rules are valuable. I don't want to look at these rules. I want to get this start from this graph. I want to go ahead and apply do Z, do X. Z, X, do Z means remove all the edges that go into Z. I don't have anything going to Z, but I have something going to X. This one, this one, this one, and this one. Is this correct? Yeah. All right. Let's take a look at what we have here. I want to see whether I can remove one of these do operator, one of these do operation. Guys, one thing that matters here, under what case this is equal to this? Under what condition? When we have a randomized control theorem, right? Correlation and causation are the same. When we have no confounder. I'm trying to give you intuition, the highest level of intuition. That's how you should actually think about this. Causation and correlation are the same when there is no confounder, right? When there is no effect of confounder here. Now let's go back here. Means I can replace do with C. Think about Z. Is there any confounder from Z to Y? No. No. There is just a direct path. There is no confounder. So causation and correlation are the same. I can just go ahead and get rid of that. That's how you should think about this. That's how I would think about that. These rules are important, of course, for a complete graph. You have to put the complex graph. But that's how I think about that. And if you think about this, now go to the intuition mode. X bar, remove everything I'm going to, and Z underline, line underneath Z. Means remove all the edges that are going out of Z. In a sense, we don't want Z dictate any child node. In a sense, do and C are the same because the do doesn't really matter here. That's another way you can actually improve your intuition. Do operator means that I'm gonna set the value of the Z to little z. That's another way to look at this problem. The way I look at that is this. We don't memorize anything. We just apply the do operator and then go from there. Another way, intuition. This doesn't help. I see a lot of websites use that. Maybe it helps you. Guys, this expression is correct regardless. Go ahead and remove this. And then ask yourself what's going to happen. Let me do it for you. Let me see what. A lot of people say that, hey, go ahead and assume X did not exist. You get this. Right? Under what case? Under case that are independent of each other, given W. Under. But that's obvious, right? So in a sense, you're trying to say that Y and Z are independent, given W. Like in a sense, you're getting rid of the impact of the confounders, right? On the when you remove all the rows that are going out of Z. So what does this remind you is that that's like effect of causation and correlation. I'm just removing the do operator, but that's more or less the same thing I'm telling you without even removing the do X. This rule is valid. We all look at that. The rule is valid, but I was trying to give you an intuition that always start with this do operation and then try to make a reason here. You might want to say to yourself, hey, I could say a lot of other things as well. Absolutely. We are trying to stay in the rule of action, observation, exchange. Based on this graph that I have here, this G2, you are able to say that, okay, I can remove do Z and convert it to the Z. That's also another way to look at this. If this do X did not exist, if the variable X did not exist, then you can actually go ahead and say that, okay, do Z is equal to this. I want to make sure that everyone follow what I say. ZWY. Remember, X doesn't exist. If you have this G3, right? So in a sense, do Z, doing intervention, is the same as seeing Z, right? Because there is no confounder here. There is really no confounder. So if you condition on W, Y and Z are independent. This blocks, Y blocks this, W blocks this path. Do you guys see what I'm saying? W blocks this path, so Y and Z are independent. That's another way to see this one. Okay, now let's go over rule 3 with each other. Rule 2 is the hardest one. Trust me, rule 2 is the hardest one. And then let's go to rule 3. All right, rule 3 means what? Insertion and deletion of. Rule 1 was the insertion and deletion of observation. Rule 3 is insertion and deletion of actions. Very important. They are all important, but some of them you can use them more often. Action. Remember what's actions? What's action? Action is a do operation. And observation is anything that doesn't have to see. All right. What does this rule says? In my opinion, it's very intuitive rule. It's just we need to define some stuff for you. It's a probability of y given to x, given to y, given w is equal to probability of y given to x and w. I remove I removed the z. I didn't change it to a z. I remove it. Insertion and deletion of action. Do z is removed. Under what case? If y and z are independent, given x and w, in what graph? In a graph that remove all the arrows going to the x and this is very important. What does this one mean? This requires a definition. I will go over the example for you guys to see that. Any z node that is not ancestor of w. So remove any edges that go into the z as long as that z is not ancestor of the w. And what does ancestor mean? Ancestor, you can think of it like as a parent of w or parent of w. Then you can think of it as an ancestor here. All right, so that's actually very, very important thing. So we look at the example, but remember, just look at this equation. Do is removed as opposed to what you had before. Do, the whole do operation is actually removed. Do of z is removed. All right, let me just show you a graph here, a couple of graphs here for you to gain some intuition. The G graph is that you have some sort of z, you have some w, you have some x. Let me. We have some y, and then that is going here, and then that's it. So guys, let's see what's going to happen to this graph, modified graph here. And how to construct it. Step number 1. Go ahead and get gx bar over. First, construct this graph. What's going to happen to this? Go ahead and remove any arrow that going to the x. Do we have any arrow going to the x? We don't. That's a step number 1. Go ahead and remove any. Let me just. So this is for this one. This part is z, w, x, y. This is gonna be gx bar. Then step number 2, go ahead and remove any arrow that going to the Z as long as Z is not ancestor of W. Is Z an ancestor of W? Yes, Z is a parent of W. So do not remove the arrow that going to the Z. If Z is not ancestor of the W, go ahead and remove the arrow that going to the into the Z. So this graph actually remains like itself. All right. So that's gonna be this expression. So this expression, this equation says that, you know what? In this final graph, this one that we see, are Y and Z independent? Yes. Y and Z are independent, given W and X. So you can just go ahead and remove do Z. For this graph, you can just go ahead and remove do Z and completely replace it. Very powerful, right? Okay, that's good. Let me give you another example just to make sure that you're familiar with this. I'm gonna call it G2. So G2 is gonna be Z. Now I'm gonna switch some of the arrows here. W, this is gonna be this way. It's gonna be this way, and then it's gonna be this way. Okay, great. And then let's construct this one. G2 X bar first. Go ahead and remove any arrow that pointing to X. So this one is gonna be removed. We have the X, Y. After you get familiar, you can just do it in one iteration. You can just, okay. Now go ahead and remove any edge going to the Z as long as Z is not ancestor of W. Is Z ancestor of W? No, Z is a child of W. It's not. So go ahead and remove any arrow that going to Z. W to Z is removed. So we have Z here, we have X here, we have this here, and then we have this is W, and we have Z here. All right, so Z is actually completely independent of Y, independent of actually everything here. So this, you see that this the same thing here is applied. You can go ahead and remove do Z from this, right? It's a powerful theorem. It's very, very powerful. Now, I want to tell you more how I think about this one. This is all great, but how would I think about this problem here? Um, like, what's the way that I'm actually looking at this problem? Okay, so I start with one of these graph. I think this one is a good one, and I set it here. Let me see if I want to start with that one. Yeah, I start with this one. Why not? All right. So I start with this one. P of Y, do X, and do Z and W. What's going to be equal to? First, go ahead and construct a graph for this. You get Z. Any edges that going to Z would be removed. Any edges going to X also will be removed. All right. So this one. Great. And any edges that going to, okay. So I have this. Okay. Now let's take a look at what we are going to do here. This is very, very actually important thing. We have edges that going into the Z is removed and edges going to the X is removed. Guys, if I'm condition on, I have a do X, and if I condition on W, don't you think that Z and Y are independent? Remember what we are saying, that always look at the every expression, look at every node to see if they are independent of Y or not, because Y is in the left-hand side of the expression. I condition on W, Y and Z are independent. So that's it, just remove it though. That's it. I don't need to construct that. But I want to tell you something, guys, here. So maybe some of you will say that, okay, you already know that. Why not? Why don't we remove X? But X is connected to Y, directed path. Okay? So that's how I think that. These rules are important, but it's important to have an intuition. You cannot just put these rules in front of you and then keep doing every causal derivation. At some point, these rules become your second nature. All right, fantastic. Now that we know the rules, you're so powerful that you can drive any do-free expression as long as the graph is identifiable. Remember, okay, this is great. Now I want to drive the do calculus for you using drive the backdoor criteria using do calculus. Remember, guys, we have this. Yeah, X. Remember, we said that probability of y given to x is equal to this. Oh, I don't want to spoil that. Let's not spoil this. Let's not write the final answer. So we are going to start with this. We want to calculate the backdoor criterion using do calculus. That's our goal. Okay, guys, from the law of total probability, what do we have? We have this. It's called probability of y do x given z. That's probability z given to x. That's all we have. Okay. Now let's see what we can do here. Now I want to see what we can do. Okay, we calculate, we derive all the stuff using a special operation. And you all have seen that actually using a special operation in the second video. We didn't talk about do calculus. Now I want to talk about the do calculus. What sort of rules? Two different pieces, this one and this one. What should we exactly do here? All right, let's take a look at that. What do I want to do? I want to calculate the result in such a way that do operation is not really involved. That's what I want to do. All right. Remember, which one was the case that the do was removed among the rules? I am gonna go and look at that. First, starting from rule 1. Guys, rule 1 has a do. It's not rule 1. Rule 2, the do z becomes z. I want rule 2. Okay. I want to get rule 2 because I don't want to see this do x here. So I apply rule 2 here. Let's apply rule 2. What was rule 2? Under which graph we have? Under which graph? We say y, remind you for rule 2. Rule 2 was that p of y given do x do z and w is equal to probability do y given do x and w given y and z are independent. Given x and w for the graph of x bar and z under. Okay, so that's great. This is fantastic, guys. So one thing you need to realize is that we have only one do here. We have only one do, and let's forget about this x from here because we don't want to at the end have this. Let's forget about this x here as well. Let's forget about this one. So unless we're gonna put this one in the different format. All right, good. Oh, I don't know. Okay. Rule 2, we don't remove anything. We just put it here, z and w. And then x is gone as well. Right? Okay. Remember, we just have one do here, though. That's what I'm trying to say. All right, so guys, let's go ahead and here we are talking about x. So like you can actually replace everything with x if we want to be consistent with this one. So do x, 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 and x. Okay, so I am gonna go ahead and construct, remove any arrow that is going to out of x. I'm gonna create a great. Is y and x independent of each other given z? Here we are having a z instead of w. Is that correct? Yeah, we condition on z, they are independent, right? So this w here, if you want to map everything to this, is z actually. If y and x independent given z, you condition on this. You condition on this. Y and x are independent, right? So in that case, do x become x. That's it. This part become p of y given x and z. As simple as that. Now we have this. But I think my derivation in part 2 was even simpler. What is p of z given do x? Okay, what rule do I want? I want to get rid of do. I want to get rid of do. Which rule we get rid of do? It was rule 3, right? So for this one, so this one was rule 2. For this one, we're going to apply rule 3. What was rule 3? I'm going to write it in the language of Python to make sure that people don't get really confused. Okay. So 2x is equal to p of z. We remove do. We completely remove them. We don't really make it c, right? Given what condition is valid? Given what condition is valid? So I'm gonna, given what condition is valid, do x given that y is independent of the z, the whatever variable that you can completely remove that, given the other variables. Okay. So here z would be independent of x. Z would be independent of x. In what graph? I will specify this later. In what graph? In g of, again, I'm gonna go up for you guys to see this. After they do this multiple times to get really familiar. Remember, we are actually we are doing the do on x. So this part is whatever we are doing do on that. And this part is whatever we are getting rid of that. So what is the variable that we are doing do on is x. What is the variable that is gonna show up here? So this one is whatever variable we are doing do on. This one, so it's gonna be x bar. It's gonna be x bar. So this is gonna be x bar. All right, we are asking if z and x are independent of each other, given y. No, if z and x are independent of each other, given no variable. Is this correct or not? If z and x are independent of each other, y is collider. We are not conditional on collider. The path is already closed. The path is closed between z and x. Y is collider. So if this is collider, this means that we can get rid of this do operator. All right. So then you can actually get the final expression here based on this p of y given x and z times p of z. And that was the condition, that was the idea of a do calculus. It was a little bit more complicated than what I threw for you guys in the part 2. It's because it's really complicated with the if it's the first time that you're seeing actually these rules, and also you need to be familiar with the collider, a little backdoor path, but it becomes second nature. So as an exercise, I want you guys to calculate the front door criterion using do calculus. So drive front door criterion that we drive in part 2 using do calculus. Hint, you have to repeatedly apply rule 2 and rule 3, right? It has involved some marginalization as well. And if you have a question, leave a comment under this video, and I can actually post a video on a derivation of front-door criterion using do calculus. All right, so this video actually is getting pretty long. That's it for this video. If you like it, please like and subscribe to the channel, share it with your friends. And I really would like to see actually what's your feedback on this video series. It's a little complicated, but I think it's very, very important and worth it. Next, I'm gonna post a video on how to convert, how to go from potential outcome to causal graph and vice versa. They are exactly equivalent. I told you in the first part of this video series. But that's it for now, and wish you best of luck and see you all in the next video. Thank you.